Fix S, a non-empty set of positive integers. Say that n is clean if it has a unique representation as a sum of an odd number of distinct elements from S. Show that there exist infinitely many non-clean positive integers. Say S equals Sn for Si greater than 0 and Si in C, I guess in N, has a unique representation as a sum of an odd. Wait, can we turn this into a combinatorial problem? Unless S is infinite. Unless S is infinite, I think we can turn it into a combinatorial, which means if S is finite, we have a finite number of clean integers, which means we have an infinite number of non-clean integers, which means we have to look at the case when S is infinite. Yeah, so we have to assume that S is infinite, and if we S0 odd number of elements, what goes wrong if it's an even? Oh, wait, maybe it doesn't matter whether we restrict it to odd or even, but it matters that we restrict in one fashion or another. For example, yeah, what I'm thinking is going on here is that the restriction actually gives us a greater number of clean numbers, because there could be a representation with an even number of distinct elements of S, and there could also be a representation with an odd number of distinct elements from S. But as long as there are no other odd number of distinct elements making a representation, it's still clean, even though there exists an even number, 1. So for example, like 1, 4, 5. So with the set 1, 4, 5, 5 is still clean, even though it's also a sum of 1 and 4. What if we have S equals 2 to the I? If we have S equals 2 to the I, then if we did not restrict it to an odd number of distinct elements, then it would make the whole natural number, the whole of natural numbers. Yeah. And we can't do the same trick with like 3 to the I because of the distinct keyword. Like in the case of 2 to the I, there are clearly an infinite number of numbers that don't have a representation. But how to show there's not something else that breaks it? Okay, so since this is asking us to prove the an infinite number of the complement, if we call this fancy C of S the set that is the clean numbers generated by S, then we're essentially being asked to prove the cardinality of the complement of S is infinity. So this seems like a proof by contradiction. If we assume there are a finite number of them, a finite number of numbers that have a unique representation as a sum, a finite number numbers that don't have a unique representation as a sum of an odd number of distinct elements from F. Okay. So actually, I'm going back to the 3 to the I set, because we can't do 2 times 3 to the I, because that would be a sum of non-distinct element. But what if we modify it slightly so that we have 1 and then 3, 1, 2, 3, 4, and then 3 to the I minus 1, 3 to the I plus 1, because that way when we add them we get 2 times 3 to the I. So what breaks here? And then to get 3 to the I, we just do 3 to the I minus 1 plus 1. But then 3 to the I doesn't have a unique representation. So wait, does it? Is there some way to get 3 times 3 to the I from this? I think we need 3 to the I in there as well. That way we can get 3 to the I times 3 by adding 3 distinct elements. And so 3 to the... Yeah, now it's a uniqueness problem. But if we include 3 to the I, and we include the ability to do 3 times 3 to the I, then it's not unique. Yeah, yep. Alright, so this definitely, based on the construction of the problem, it seems like a proof by contradiction might be the right direction, but I'm not sure exactly how I would construct the assumption. Like, we want there to be a finite number of non-clean positive integers, which means what? How does that relate to the clean integers? There could be an infinite number in either case. So we can't just say that means there's an infinite number of clean integers. Finite of things that don't have a unique Okay, so I'm gonna try and represent this set fancy C of S as okay, I've got S0 plus the sum from I in, I don't know, NN for SI1 plus SI2, S0. Okay, I'm gonna assume that S is just organized in increasing order. So there doesn't exist an item in S smaller than S0, which means S0 is clean. And it also means S1 is, and it also means S2 is. S3 we don't know is because it could be the sum of S0, S1, and S2, in which case it's not clean. However, I think if S3 has any elements that aren't clean in it, is it possible for the number of non-clean integers to be finite? I don't think so, because because you always have that S3 and other representation of S3 as interchangeable. So anything that includes S3 would then not be clean. So you would then have an infinite, which means we can safely assume, without loss of generalization, that all of the elements in S are clean. So none of them are the sum of any odd number of distinct elements of the rest of the set. So all of the elements in S are clean, which means we should, so S0, 1, and 2 are clean by construction. But it also means S3 cannot equal S0 plus S1 plus S2. S4 cannot equal S0 plus S1 plus S2. It can't equal S0 plus S1 plus S3. And it can't equal S0 plus S2 plus S3, and it can't equal S1 plus S2. S5 can't equal, I'm just writing the first few numbers in the sequence to see if there's any pattern. Right now we have 4 restrictions on S4, 1 restriction on S3. We're going to see how many restrictions we have on S5. S0 plus S1 plus S2, S0 plus. Okay, so all of the restrictions in the previous step still apply. So I don't have to rewrite, which means the next layer is just going to have S4. Yeah, that's what I'm thinking. Okay, so we have 1, 2, 3, 4, 5, 6, 7 new restriction, which means we have 11 restrictions on S5. And if we keep doing this, the last element is fixed for the sets of 3. Yeah, so let's look at the set of 3. Wait, I think the sets of 3 is the sum of the triangular numbers. 1, 1, 4, 10. 1 plus 3 plus 6. Yeah. I think the sets of 3 is the sum of the triangle because the last element is fixed. So the possible number of restrictions is going to be n minus 2 choose 2, which is n minus 2 times n minus 1 over 2. But what about the sets of 5? Yeah, the triples should be a sum of triangular numbers because each layer is going to have a triangle number of new possibilities. But I will write them all out this time, and then I'll probably stop writing them after 6. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 new restrictions. So we get 26 restrictions on S6. I'm gonna split these up into number of elements in the sum. So we have 0, 1, 0, 4, 0, 1, and 10. I'll just 1, 4, 1, 10, and then 5. How many were the 3, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 1, 1 plus 3, 1 plus 3 plus 6, 1 plus 3 plus 6 plus 10. So you can see that it's the sum of triangular numbers. And then here we have, oh wait, did I miscount? 1, 2, 3, 4, 5. Oh, I miscounted. This should be, and this is 1 plus 5. For S7, we have 5, choose 2. That represents the number of triples in the new restriction. We have for the new sets of 5, we have S6. It's going to be like S0 plus S1 plus S2 plus S3 plus S6. And we're choosing these 4 from the first 6. This is 6 choose 4, and then we get 7 choose 7 for the set of 7 that is there. So that gives us 10 plus 6 factorial, 4 factorial, 2 factorial. That's 5 times 6. 5 times 6 divided by 2. Okay, 15 plus 1 is 27. Okay, I think we may be onto something here, because the last one was 26. One before that was 11. One before that was 4. One before that was 1. So this one will be 53 in total, because this is how many we're adding. And S8 will be 6 choose 2 plus 7 choose 4 plus 8. Wait, yeah. 8 choose 6. 6 choose 2 is the same as 6, 4. So we get 15 plus 5 times 6 times 7 over 6. That's 35. Plus 7 times 6. 7 times 8 divided by 2. So that's 7 times 4 is 28, which is 78. We have a formula to work with. We have Sn. Actually, I'm going to split it into odds and evens because they behave slightly differently. With odd numbers, S2n minus 1, we get the sum of 2n minus 3, 2n to I, beginning at 2n minus 3, right? 7 choose 2, 8, 4, hold on. It should be 7 choose. Fixing S8, there are 8 remaining, and we're choosing 4 of them. So it's 8, it is 8 choose 4. And for the sets of 7, we're fixing S8, we have 6 remaining out of 7. Okay. I think I may have done something wrong. For these sets of 5, we're fixing S6 here. That means we have 0 to 5, which is 6, we're choosing from. Okay, yeah, I did something wrong here. This should be always 6. And so what we actually get is, yeah, this makes more sense. And then here we have 7 choose 2 plus 7 choose 4 plus 7 choose 6. And this is 8 choose 2 plus 8 choose 4. Yeah, plus 8 choose 6 plus 8 choose 8. Now, this is going to be a sum over all of... Wait, is there some kind of a identity even index choose functions? I feel like there is. Yeah, so that's what I'm getting to, but we don't quite get... Yeah. So the problem, so we know that the sum of each row in Pascal's triangle is 2 to the r for row r. But we only have half of it. But is it exactly half? Ah, yes, it is exactly half. Excellent. Okay. Yeah, that's what my intuition was telling. Okay, so in that case, if we add them all, yeah, so 1, 4, 15, we get 1 choose 1, that's 1. 2 choose, oh no, it was 2 choose 2, that's then 3 choose 2, 3 choose. All right, I'll make sure to take a look. See, it's about 4 o'clock. Yeah, I have to probably head out in a couple hours anyway. So, but I think I'm almost through, and then we get, but it's not exactly half, because sometimes we miss the first element. 4 choose 2 plus 4 choose 4 equals 7. Yeah. Oh, but this is interesting. 137. So it is always 2 to the k minus 1. It seems, or I guess 2 to the k minus. 5 choose 2 plus 5 choose 4 is 10 plus 5, which is 15. Yeah. So it's 2 to the k minus 1 minus 1. And we're summing over all of them. 2 to the 1. We are growing exponentially, but is it fast enough? I think so. Because when we add the next term, it's always going to be more than 2 times the previous one. We have sk plus 1 is greater than 2 times sk. And that's what we wanted to show, right? Wait a minute. The number of restrictions is greater than 2 to the twice the previous. But sk plus 1 doesn't necessarily have to be greater than all of the restrictions. So that's a case we have to deal with. So I'm going to start by construction. Say we start with 1, 2, 3. We can't do 1. And this is S0, S1, S2. And so that tells us that S3 is not the sum of all of those. So S3 is not equal to 1 plus 2 plus 3, which equals... So that means S3 can equal 4. So the next set would look like this. And S4 cannot equal 1 plus 2 plus 4. It cannot equal 1 plus 3 plus 4. And it cannot equal 2 plus 3 plus, which is 7, 8, 9. But it can equal 5. How crazy is that? Okay, so it can still be 5 because we don't care about the even. We don't care about the even representation. So it doesn't matter that 1 plus 4 is 5 and 2 plus 3 is 5 because 5 is the only way to do it with an odd number. So 5 is still clean. S5 cannot equal the sum of all of them. It cannot equal 1 plus 2 plus 5. Oh, wait a minute. Uh-oh. So I think there may be a secondary condition that I missed in the construction. How do we prevent this kind of thing from happening? This kind of thing happens because 3 plus 4 equals 2 plus 5. Stop it. Equals 2 plus 5. And so this thing this kind of thing will happen when S of I plus S of k equals S of j plus S of n, which means we need to make that not true to be able to construct this set, because otherwise it produces non-clean results, which means when we have 1, 2, 3, we already have something that equals 5. 2 plus 3 equals 5. So we're also restricting, it can't be 4, right? Because then we have 2 plus 3 equals 1 plus 4. So it can't be 4 because we know this has to be an infinite set. Wait, are we gonna end up getting the Fibonacci? No, because, wait, maybe. That would be kind of wild. S4 can't be 1 plus 2. Wait, it can't equal 4, but how do you make 4? You can't make 4. 4 is not clean. Okay, let's just continue. Maybe we'll only get a finite number of them, but I doubt it. So S4 can't be 1 plus 2 plus 5. It can't be 1 plus 3 plus 5. And it can't be 2 plus 3 plus... So this is 8, 9, 10. And 6 is already included. Now we have to test to see if... 7 works. And the way we do that... 7 doesn't work because we have 3 plus 5 is 8, and then 1 plus 7 would also equal 8. So it also can't equal 7, which means the next possibility is 11. Now, if we add all of these, we do get 11, but that would be 4 numbers. Yeah, that's fine. If we get 4 numbers that add up to another 2 numbers, that also wouldn't be allowed. But we don't have that in this. So we can add 11. And I still want to keep this in the back of, up our sleeve, basically. Because I think it will become important when we determine which ones are not clean and if there are a finite number of them. So S5 cannot equal 1 plus 2 plus 3 plus 5 plus 11. It can't equal 1 plus 2 plus 11. It can't equal 1 plus 3 plus 11. It can't equal 1 plus 5 plus 11. It can't equal 2 plus 3 plus 11. It can't equal plus 5 plus 11. And it can't equal 3 plus 5. So 1 plus 2 plus 3 plus 5 plus 11 is 16, 19, 20, 22. This is 14. This is 15. This is 17. This is 16. This is 18. And this is 9. Hi, e to the 2 pi I. 2 I pi. How you doing? Okay. So now we have to check if 12 and 13 are okay. I suspect that they aren't. I suspect they aren't. With 12, well, they're tricky. I think we have something that works for this problem. I think we have something that works. I'm just trying to construct an explicit example to convince myself. The work that I have so far is that the number of restrictions for each element of S grows greater than 2 to the k, which intuitively should mean that there are an infinite number of non-clean integers. But I realized that the the newly added item, doesn't have to be greater than the restriction. So I'm constructing an explicit example to see if I can discover some other property that would assist in the proof. And I did. We have the sum of any even number of numbers can't be equal to the sum of another set of even numbers. Now, like, I'm worried about 12 and 13 in this scenario. If we add 12, what break? 1 plus 12 is the same as 2 plus 11, so that's why that breaks. And 1 plus 13 is the same as 3 plus, so that's why 13 breaks. At the same time though, 12 and 13 have no representation. Okay, I'm starting to convince myself that SK has to be greater than all of its restrictions, because the possibilities that aren't included in the restrictions don't work. They end in a dead end, like 12 and 13, like 4. Like, they'll work at the moment, but as soon as we add another element, they won't, because then we have two sets that equal the same thing. And okay. So then we also have that the sum of S2I for I in the natural number cannot equal the sum of not the natural, for I in a set I cannot equal, no, it's an even number of numbers. It doesn't have to be even in this. Okay, so we have the sum of Si plus Sj for, hi Ronaldo, how you doing? Okay, how do I know what I'm trying to say, I just don't know how to write it down. uh we need, it's gonna be like a nested sum for Si plus Sj for a not equal to j, and ik, and then ik is not to jk, and then we iterate over ik jk is in I, an index set, and we cannot have that equal to ik jk in j, another index set for ik not equal to jk, sik plus sjk, where with the intersection, basically the two index sets being disjoint, so that you don't get and this is for all ij, such that they are disjoint, so that avoids repetitions. Okay, now, but then the places where this is true and thus excluded from the clean set, that is an infinite set. And these are non-clean integers because they don't have representation. So what this construction does is it makes sure that all of the elements of S are clean, and all the elements generated from the elements of S are clean. So every representation of every sum of a distinct number of elements in S is also clean. But that causes there to be an infinite set of numbers that don't have a representation. How do we prove that this is an infinite set? I, K, J, K in I of the sum from S, I, K plus S, J, K for I, K not equal to J, K has no representation. Oh wait, no, that's not true. It's not true. That has no representation. 12 failed. Our set was 1, 2, 3. Come on, 5, 11, and 12 failed because 2 plus 11 equals 1 plus 12. So it's not that this has no representation, it's that SK plus this has, no, wait, 12 has no representation in this set because we can't add it, and it's not included in the level 1 restriction. And yet we're able to include 5 when the restriction on S3 was 6. Okay, I may have figured it out. Since we included 1 and 2 in this set, then the first restrictions of the next SK will be 1 plus 2 plus SK minus 1. And because of this, SK minus 1 plus 1 never gets a representation. Never in this construction. Because then, if it did, 1 plus SK equals 2 plus SK minus 1. And we can't have that. And since S is an infinite set, there are an infinite number of. So 1 and 2 cannot both be in the set. Is there a construction that doesn't include 1 and 2 both being in the set? If we start with 1, 3, 7. If we start with 1, 3, 7, then S3 cannot equal 1 plus 3 plus 7, which is 11. If we include any SK that is 1 greater than the previous one, any at all, then we have the same problem as last time, where so let me write down what I'm thinking here. I'm gonna get rid of this. If there exists I and j in N such that Si equal or plus 1 equals Sj, then for k greater than I and j, Sk plus 1 cannot equal Sk minus 1. Wait a minute. Sk plus 1, and SK plus 1 has no representation. But that also gives us that no matter what we do, SK plus 1 has no representation. We cannot include it in the set because then we get this problem. But if we don't include it in the set, we still get this problem by construction. If we necessarily exclude the next one in the sequence, like if we necessarily exclude SK plus 1, voice break, if we necessarily exclude SK plus 1, then that number is not going to have a representation because it's not a part of our original restriction system. So no matter what we do, we get that SK plus 1 does not have a representation. And since S has to be infinite, that implies there are an infinite number of non-clean integers. QED.